And then we calculate F sub SL, friction factor of based on superficial liquid velocity. S C sub SL, how much is that? What is C sub SL? How much? 1 for laminar flow and something else for turbulent flow, right? Where do I get that from? It is the same. It is the Blas's type equation. If you look at the Blas's type equation, everything is here. Constant equal to 0.046 if it is turbulent flow. So friction factor, finding friction factor is constant multiplied by Reynolds number, and this Reynolds number is to the power of minus n. So constant is 0.046 if it is turbulent flow, otherwise it's 16, right? And the exponent is 1 if it's laminar flow and 0.2 if it is turbulent flow. So this formula is the Blas's type equation for friction factor for the case of smooth pipe. Okay? It is just long, but it's step by step. Okay? So once I have, then 0.046 something, right? That is C. And N is probably 0.2. Okay? So this is based on the value inside. Rho, VSLD, over mu. That will give me the Reynolds number based on superficial liquid velocity. So I get F sub SL. Okay. After I get F sub SL, put everything together, I get minus dPdL sub SL. Good. So to know whether it's turbulent or laminar, I have to check on Reynolds number of liquid film. Okay. Check Reynolds number of liquid film is more than 2100. Then C will be 0.046 something and N is 0.2, previous slide. Okay. Then we can calculate the top part. Oh, it's not the top part yet. Okay. The top part of xm squared. Okay. Alpha C. Alpha is the void fraction. Here's the formula. VSG over VSG plus VSL FE. VSG is known, right? VSL is known. FE is calculated already, so we can get this. Rho C, average density of the core, is a weighted average based on the alpha C. Alpha C rho G plus or minus rho alpha C rho L. Same thing for mu C, core viscosity. And superficial core velocity. VSC is known, VSL is known, F is calculated already, previous page. This is F. It is just a bunch of formula, right? Yes?
So can't you just say you could put a pressure gauge on the wellhead, a pressure gauge on the separator, you get 2 different pressure readings, subtract the 2, pressure drop.
Ah, that is the pressure drop. Yes, sir. That, yes, we can. But what if I plan to have a well? Okay? And let's say I work at a service company, I try to make the software. And the software will tell, hey, this well we produce based on the IPR, it will be annular flow. If I have annular flow, this is that much pressure drop. I have to do the calculation before I build the well, right? Before I do the well. How do I do that? This is how I do that.
How would you be able to really know what your, like through models, what your film length is? Like how would you be?
In the well, that's a good question. In the well, we have several flow patterns can occur, right? Several flow pattern mean some part of the well may be near the top, it may be annular flow. Near the bottom, maybe slug flow or something. How do I know which part is what? So this means I have to discretize it, generate the flow pattern map every time that I move. So when there's a pressure drop, I get the new fluid property. Some gas may come out from oil, right? Gas come out of solution. We have more gas as a pressure drop along the well. So gas come out, pressure may change, so gas density change. So we have a new fluid property. Then we can use this chart again. We can calculate the new y value, new x value. So after the discretization, we determine the pressure drop of the flow pattern every time. When we know what kind of flow pattern is that, then we use the method below to calculate the pressure drop according to that flow pattern. It cannot be done by human, okay? It has to be programmed and have computer do it because it's a lot. So if I have a well very long, I divided it into 2 sections. Maybe human can do it. If I divide it to 20 sections, I cannot. So I have to program it. And okay, section 1, step 1, do the flow pattern determination. If it is annular flow, calculate entrainment fraction F sub E, okay, based on the new value of every time that we flow. So we reach the new point. The volumetric flow rate change. Okay, F sub E, you see this VSG. VSG is a volumetric flow rate per area, right? We will get more gas coming out of solution every time that we have pressure drop, right? There's a phase change. That has to come from thermodynamic package. Okay, from the thermodynamic package, it tells at the equilibrium what is the fraction of liquid phase, fraction of gas phase, how much gas come out from liquid phase. After that, we can calculate the new value of entrainment fraction. So it has to be done every section in the well. Okay, good. And the way that it do is use this kind of step. Okay, it's just a step in the calculation. After we know VSC, then we can calculate FSC. Friction factor based on superficial core velocity. 0.046 multiplied by that value pre-calculated to the power minus 0.2. Then I calculate 2F rho C VSC square over D. Then I can get XM square, right? Okay. You cannot do in the exam, even though it is easy. You can do it in the Excel, okay? But in the exam, if I miss one number, everything else is going to be wrong. Not fun, right? Is it? Not fun. I won't ask you to do it in the exam. Don't worry about it. But I have the way to test you, okay? So x sub m square multiplied by 1 minus f e to the power of n minus 2. It's just a formula. So I get xm0 square. Ym modify dimensionless height. It's just delta rho g something. So everything is calculated based on the pre-calculated value. Then I can look at the chart. Okay. After I know xm0 square, I take the square root. I look at the chart. Let's say I have upward flow and ym is 100. Okay. X is 0.3. I go up, reach the line, look on the left. Then I get dimensionless film thickness. Good. Use ym and xm0 previously calculated to determine dimensionless film thickness. Dimensionless film thickness is the film thickness over pipe diameter. After I do this, okay, determine phi sub c from this graph based on the obtained value of dimensionless film thickness. Dimensionless film thickness, I get about 0.035. Okay. 0.035. So I start at 0.035. 0.035 may be about that. And I look at the value of, I go up. You see this line? Just one line. Don't use another part because it's more difficult. So that line is a line to read phi c squared. So when I go start from 0.035, I read this line, then I go to the axis, then I can get phi c squared. So phi c squared may be about, how much do I get? Between 10 and 20. So maybe over there is 15. So, can you read this? Something else, like this part, is a distraction, don't use it. It's not a distraction, it's a more difficult way of doing it. Don't use it. Use just this line. 5c squared. Read dimensionless film thickness, 0.035, go up, that line, go down, and read 5c squared. Take the square root, then we get 5 sub c. Okay. So 5 sub c will be, 5c squared is that term. See this? So once we know that, what do I do next? Minus dpdl sub sc, frictional pressure loss based on superficial core velocity, which is known, right? Minus dpdl sub sc is known, but it's not the real pressure drop. Okay, it's not the real pressure drop, but it's known. So that is known. Core density g sine theta, that term is known, and that term is known. Okay, I rearrange it, then I can get minus dpdl sub c. Okay. Actual pressure drop along the core. Okay, actual pressure drop along the core minus dpdl sub c has identical value to minus dpdl sub f. Okay, pressure drop in the core per unit length and pressure drop in the film is the same. We can get from any of that. So once we get that term, that equal to our pressure drop per unit length. Done. Good? Okay. What can I do to help you? What I can do is this. I can say, hey, I give you the table. I put it in Excel already. I tell you, okay, VSL equal to this much, VSG equal to this much, F equal to that, phi equal to that, Reynolds number, every parameter equal to something, something, something. I even calculate all this for you, and then I let you read the graph. Okay? When you read the graph, you read two graphs, and all this is calculated already. If you still cannot do that for me, that's not my fault because I calculate most of the items for you already. You just read the graph, move this to that side, plus that term, done. Good? Easy enough, right? For slab flow, maybe it's a little bit difficult. Good, we're done. Question? Question. Okay, I have a question. Stephen, why do we have to? What is the big picture of this? Why do we want to know anything about multi-phase flow? Why do we use it? Why do we use it? Or when do we use it? What is the final answer that we want to get from all these lectures? Pressure drop. Very good. There are two things. Flow pattern and pressure drop. Okay? Just that. We do all these painful things just to get pressure drop. Okay? It's used for during the planning phase, not during the production phase. Because during the production phase, like what he said, we can measure the pressure and that's it. But we may not be able to do that for the unknown project, right? Some new project, you need something like this. Okay? Mechanistic model is good, but it has some formula from experiment. There's some empiricism in it. For example, even another flow. You see entrainment fraction F sub E. That is empirical correlation based on the experiment. Of course, the force balance, that is physics, right? Momentum balance. Okay. but there's something unknown like the film thickness or something or entrainment fraction. That is based on the measurement. There's some a little bit unknown in it. Okay, that's come from experiment. No more question? Okay, let's move on. The next one is gas treating and dehydration. Okay, to treat the gas, two main processes that you should know for the exam. Gas sweetening process and gas dehydration. Okay. Amine power is for remove water or remove acid gas. Amine tower is for gas sweetening. Okay. Amine process is gas sweetening. Glycol process is for dehydration. Got it? Glycol is to remove water. Amine is to remove gas. Of course, there are some other process that is important too, but the main thing is gas sweetening and that dehydration. Amine unit and glycol unit. The step to do this before it reach the gas plant. Okay, you should have gas treating, gas dehydration. Okay, gas processing is to be done at the gas plant. Gas processing is what? When I say gas sweetening means remove acid gas. Dehydration means remove water. These two can be done at the tank battery. Gas processing is mean do cryogenic expansion, NGL, nitrogen removal or something. Those things has to be done at gas plant. You cannot do it on the field. Okay. If you have gas well, it's sound, it has some water. What do we do? Step one, of course, separator, right? Separate gas out. After we separate gas out to meet the pipeline specification, we have to remove. Do we remove acid first or we remove water first? Acid. Okay. We remove acid first. Memorize that. You should know that. And later on we remove water. The reason that we want to do that is acid is corrosive and it's dangerous. Okay. So we don't want that acid to corrode the pipe. It's not like every equipment has to be able to withstand that H2S. No. It's just if we remove H2S first, then the rest, it doesn't have to have any protection against that H2S, right? So we remove acid first, and then we remove water later. Okay. If it's sweet already, we may just sell directly to the gas plant. Okay. If it's sweet but have some water, we just do dehydration. Okay. Why do we have water? Separator remove everything up to everything greater than 10 micron, right? But we can have something less than 10 micron that didn't get catched by mist extractor. So that has to be removed too. That we use what? Basman? Do we use amine unit or we use glycol unit to remove water? To make wet gas, we dry gas. Amine unit? Glycol? Okay, correct. Glycol unit. Okay, this is a diagram. At a gas plant, we can also remove acid at a gas plant too. So look at this. Acid removal is the first step. Okay. First, when it comes, of course, we have like some kind of water removal from the separator or inlet scrubber. Remove any big droplet. Then we remove acid. After we remove acid, we get acid gas. Acid gas go to Claus process. Claus process convert from, yes, question.
You just said that we remove water.
We remove water later, but before we, first step is remove water from the separator. Okay, if separator is not enough to remove every drop of water, for example, something less than 10 micron. For something that less than 10 micron, we don't worry about it that much. Then we use amine unit to remove gas first, and we remove small portion of water, like 0.1 micron, 1 micron, by using dehydration. Okay, maybe I said it wrong. Step number 1, of course, use separator to remove most of water out. Then use amine unit to remove gas. Then use dehydration unit or glycol unit to remove some small water droplet or some water vapor that cannot be removed by a separator. So after we have acid gas removed by amine unit, we use Claus process. Claus process will convert from H2S to elemental sulfur, the yellow sulfur, and use that for fertilizer. Okay. So gas without sweet gas go through glycol unit to remove any water. Okay. And then we may remove mercury, we don't cover that. And we may remove nitrogen in the gas plant. Don't cover that either. Do NGL recovery, we don't cover any of that. Okay? So we focus on acid gas and dehydration or make the gas dry. On the list, we can put amine unit, glycol unit over there. It's okay. Okay? So we can do gas treating at the least. Remove H2S, CO2, okay, help to remove, meet the pipeline specification. We can do dehydration, like use a glycol unit over there. And there are some other process. How does it look like? If we have wet gas and we want to dry it, we use glycol dehydrator. It's just a glycol unit. Okay, put it over there. It's have a contact tower, reboiler, and we put it in the field. It's not that big. In oxy gas plant, you see it's a big tower, right? But when it's out of in the field, it's just okay, not that big, right? Amine unit, we can have DEA, MDEA, same that they use in the oxy gas plant, but it's not that big. Okay, if I stand over there, maybe I'm that big. Okay, good. So in the gas plant, it is a lot taller than me, right? So amine unit, we can put on the field. That's my point. Okay. Gas processing, remove hydrocarbon from the gas phase to lower it, deploy, remove ethane, remove propane, remove butane or something. That has to be done at the gas plant. Okay, we cannot remove ethane or propane at the field. Okay. What's the process? We have chemical solvent, physical solvent, and some other solid bed process. You need to know select salt because it is used at the gas plant. You need to know about MDA and DEA because it's used at oxy gas plant. And you need to know about, I think, ion sponge because it's in the exams. Okay? Just that. The rest, we don't focus on it, but we'll talk about it. It could be an exam, I don't positive, but I think ion sponge is in the exam. So there are physical solvent and chemical solvent. Chemical solvent means there's a chemical reaction. Physical solvent is not chemical reaction, it just touch it, absorb it on the surface, just that. Solid bed can have a chemical reaction on it. Okay, and there are some other special solvent, distillation, gas permeation, or membrane. We have it at a gas plant, right? So you may need to know about that too. Okay, let's talk about solid bed first. We can have several things: ion sponge, sulfate, zinc oxide, molecular sieve. Most of them attack just H2S. Molecular sieve remove everything, okay, including mercaptan. RHS. R is, I think it's a hydrocarbon chain. Okay. So it removes mercaptan. So if we use molecular sieve, the gas that's coming out doesn't have any smell. It's dangerous. Okay. So we don't know that it's leak. Solid bed. We can have a chemical reaction. Have some chemical reaction so to remove acid gas, to remove H2S. Or it's just bonding, ionic bond. It just catch, but no reaction. Okay. Let's talk about the commonly used ion sponge first. Ion sponge process, it looks like a separator. It's some kind of reactor. Okay. It's good for H2S less than 20 ppm. It's operate at certain pressure. It doesn't remove CO2. Okay. The way it works is we have iron sulfide and water produced. Acid gas go in, it react with iron oxide, and then it creates water and iron sulfide. You don't need to memorize the reaction, but you need to know what is the purpose of ion sponge. Does it produce, is it for remove acid gas, or is it for remove water? Does it produce water or something? Okay. Ferric oxide is impregnated on the wood chip. So they sell it like a bag. You put this wood chip into the reactor and you flow gas through. Sour gas from the bottom and sweet gas come out. Okay? And reaction inside is to catch the acid gas. So that's a reaction. Then we need to regenerate it. To regenerate it, we can do some kind of oxidation, make it react, do oxidize with air. So it will produce elemental sulfur and it produce some heat. After regenerated 10 times, you have to change the bed. Okay? So ion sponge, complete removal of small to medium concentration of H2S without removing CO2. Okay? Relatively small investment. Equally effective at any operating pressure. Used to remove mercaptan and convert them into disulfide or something. Just know that what is solid bed reactor to remove acid gas? Ion sponge, right? Done. Okay, next one is sulfur treat. It's similar to ion sponge, but it have other kind. It have ferric oxide. The chemical reaction that happens inside is different. It's just ferric oxide. Okay. And we have molecular sieve. Molecular sieve is some kind of different. Okay. Molecular sieve look like this. Some circle thing, very small thing. Okay. So it's a synthetical crystal solid in a dry bed. We put all these things into a vessel, flow gas through it, and then it catch any solid, any acid gas. Okay. So it can catch H2S and also water vapor. Okay. So it's operates based on the bonding. Okay. It's have the active side. So the structure is formed a weak ionic bond. So what happened here is there's not chemical reaction. Okay. It's just bonding. Form a weak ionic bond to catch polar gas molecule. Polar gas is like acid gas or some water vapor. Very good, right? We just put a bunch of molecular sieve. It's like a pellet. Put it in there, flow gas through, and gas that coming out is sweet, probably dry too. Okay. So this thing is very good. Next one is membrane. Membrane. Okay. Before you go, let's talk about membrane a little bit more. Membrane doesn't work like filter. Membrane doesn't have hole, no pore. Okay, membrane part is non-porous media. It's a polymer. Membrane has no pore. Maybe if you see the membrane first time, hey, it has big pore, small pore, and for the big pore, big molecule can go through or something. It's not like that. It doesn't work like filter. Okay. Porous barrier is just for mechanical strength to support. H2S and CO2 dissolve and diffuse quickly through the membrane, but CH4 or C2H6 and other hydrocarbon permeate or go through the membrane slower. So acid gas go through the membrane. The good stuff just go with the flow, doesn't go through the membrane. That's how separation occurs. Okay, it doesn't work like a filter. Alright, and this is how it looks like, and you have seen it over there. Membrane is very expensive, and they have to make the gas to be good enough to a certain point before they put into membrane. It doesn't have 100% conversion. Okay, some acid gas maybe will still be in the mainstream. Okay. It doesn't remove every acid gas. It's not like that. It can do like 70%, 60% or something. It's not 100% removal. That's membrane. Okay. Next one is monoethyl amine or MEA, DEA. For the purpose of the exam, memorize this. Okay. Good. And then next time we will talk more about the acid gas thing. But for the purpose of the exam, you need to know, is it lean amine or rich amine, lean glycol, or we don't have glycol? Is this one absorber, regenerator? Read about it a little bit because you have seen it at the gas pan already. We have two towers. Left one is absorber, right one is regenerator. Sour gas comes into the contact with amine. Amine take all that acid gas, and the gas that comes from the top is a sweet gas. Inside the absorber, there are several trays. It looks like a tray, and in each tray, so it goes through left, right part like this. In each tray, there's a cap to determine the pressure or something. That's too much detail, okay? But that's in amine. Very good. Are you ready for the exam? No? But you know that you have to memorize this, right? And you know the iron sponge? I think that's almost all. What time? I think I'm done. It's still 12:19. You have any questions? Otherwise, we may go. See you next time. Next time we will talk more about all these things.